In many situations, it becomes necessary to supply a balanced or unbalanced two phase or single phase load from a balanced three phase supply. One way to do, let us say, for a two phase load, to connect the two phases between two lines, this is one possibility. However, even when these phases are balanced, impedances are balanced, they will draw unbalanced current from the supply. Not only that, many two phase loads will require a balanced two phase supply as well. Some of these two phase loads are large arc furnaces or induction melting furnaces. They will can range in power, can range in megawatts. So, care should be taken to make sure that the loading of the three phase system is balanced to the extent possible. This can be done by a what is called a Scott connected transformer. This Scott connected transformer can convert a balanced three phase supply to a balanced two phase supply. If the load on the two phase supply is balanced, then the line current drawn from the three phase will also be balanced. We will see how. For Scott connection, we take two single phase transformers. Let us say here the turns is N, this turn is N2, this is the dot polarity. Another transformer with a 50% tapping, so that this number of turns is N1 by 2 and this is N1 by 2, and the corresponding secondary have the same number of turns N2. Now, let us connect this end of one of the transformers to the 50% tapping point and give balanced three phase supply to this side, it is V A, V B and V C. And let us see what happens to the induced voltages here. This is the instantaneous polarity. Here this is the instantaneous polarity. So, the three phase supply is balanced. So, let this point be M. So, let us say this is the phasor VBC and this is the phasor A, so that this is the phasor VAB this is the phasor VCA. Now, the voltage phasor VMC, VMC will be half of VBC. This is the point M, VMC. And what will be the voltage phasor VAM? VAM will be VAC minus VMC, VAC minus VMC, VAC is in this direction, this is VMC. So, the voltage phasor VAM will be this. It shows that the voltage phasor VAM is at right angle to the voltage phasor VBC. Hence, the induced voltage VA will be in phase with the voltage VAM. So, this will be the voltage VA, and its magnitude will be N2 by N into VAM, whereas the voltage phasor VB will be in phase with the voltage VBC. So, this will be the voltage phasor VB, and its magnitude will be N2 by N1 into VBC. Now, if we want the if we want the voltages VAB and VBC to be balanced two phase, that is they are already 90 degree, and if we want their magnitudes also to be same, then it is imperative that we should have N2 by N into VAM should be equal to N2 by N1 into VBC, or we want N by N1 should be equal to N by N1 should be equal to VAM by VBC. Now, from this phasor diagram, VAM by VBC equal to root 3 by 2 or equal to 0.867. Hence, number of turns should be here root 3 by 2 into N1. So, a Scott connected transformer can be obtained by two single phase transformers with turns N1 and N2. The first any suitable turns ratio N1 by N2 with one transformer having a tapping at 86.7%, the other transformer having a tapping at 50%. Now, we connect the 86.7% tapping to the 50% tapping and then give 3 phase balanced supply in this manner. VA, VB Vc, in which case we have just seen that the induced voltages Va and Vb this instantaneous polarity we have seen at no load mod of Va equal to mod of Vb equal to N2 by N1 into VLL of the primary, and Va leads Vb by 90 degree. So, this is at no load. Now, let us see what happens. So, at no load we have got a balanced two phase system. Now, let us see what happens if we connect a balanced load of some arbitrary power factor, that is we connect two impedances Z to this transformer. Once we connect impedance Z, there will be a current Ia flowing in this and Ib flowing in this. Now, this is Va, this is Vb, if these are balanced impedances, then this will be Ia and this will be Ib, this will also, the currents will also be balanced with a power factor angle of phi. What will happen to the primary currents? Let us see that. Let us say the primary currents are Ia here, Ib here and Ic here. If we neglect the magnetization current of the transformers, which are very small in any case, then Ia, I capital A will be the reflection of I small a, hence I capital A and Ia will be in phase. So, the voltage phasor diagram on the primary side is somewhat like this. This is C, this is B, this is A, this is voltage VBC, this is AB, this is CA, this is voltage AM. So, the current capital Ia, this is the neutral point of the supply voltage. The current capital Ia will be in phase with Ia. So, we can draw the current capital Ia represented by this line Ia, and the ratio will be root 3 by 2 N1 Ia should be equal to N2 I small a, or Ia equal to two by root 3 N2 by N1 into Ia. Similarly, Please note that in the secondary the current is going out of the dot terminal, hence in the primary the current must enter into the dot terminal. Similarly, for the other transformer the current IB is flowing out of the transformer, hence the reflection current IBC should be in this direction. Reflection current IBC flows through the entire winding. So, N1 IBC should be equal to N2 IB or IBC equal to N2 by N1 IB. But the line currents are not just IBC. The current IA is coming here and then it divides in two equal parts. This current is IA by 2 and this current is IA by 2. The phase current IB then equal to IBC minus IA by 2. Now, IBC will be in phase with IB. This is the current IBC. This is minus IBC. This is IBC. So, phase current IB will be IBC minus IA by 2 . So, this will be the phase current IB. Similarly, the phase current IC will be minus IBC minus IA by 2. So, this is minus IBC minus IA by 2. So, this will be the current IC. It can be easily shown that IA, IB, IC are balanced. The reason is very simple. Since IA and IB are orthogonal to each other, so are IA and IBC. In other words, IBC is at 90 degree with IA. So, the angle between IBC and minus IA by 2 is 90 degree. Therefore, the phase current IB magnitude will equal to mod IBC square plus mod IA by 2 square to the power half, but IBC we have seen it to be N2 by N1 square mod IB square and IA by 2 plus IA by 2 is N2 by N1 square into half into 2 by root 3 mod IA square to the power half. This is equal to N2 by N1 into. Now, in a balanced two phase system, mod IB is same as mod IA. So, I can say this is equal to IA. So, 1 plus 1/3 to the power half, this is equal to N2 by N1 2 by root 3 mod of IA. This is same as the mod of I capital A. Similarly, it can be shown that mod of IC equal to mod of IB equal to mod of IA. The angle between them is also 120 degree. This can be seen very easily. This is the phasor IA, this is the phasor IB, and this is the phasor IA by 2, but mod of IB we have just shown to be equal to IA. So, this length is half of this length, hence this angle is 30 degree, but this angle is 90 degree, hence this angle is 120 degree. Similarly, this angle is also 120 degree. So, we see when we put a balanced 3 phase 2 phase load on the Scott connected transformer secondary of arbitrary power factor, does not necessarily have to be unity power factor, then the 3 phase side currents are also balanced. What happens when we connect a unbalanced load? Let us draw the same circuit diagram. Now, we have connected an unbalanced load Z A to the voltage V A, the current is again I A, and another load Z B the source VB. The currents drawn here is I capital A, I B, I C. We can draw the phasor diagram in a similar manner. On the secondary side, the voltages are still balanced though, because the supplied 3 phase voltage is balanced. So, this is VA, this is VB. Now, let us say this is IA and this is IB. They are unbalanced both in magnitude and in phase angle. This is phi A, this is phi B. Unbalanced, hence phi A is not equal to phi B and mod IA is not equal to mod IB. But nevertheless, mod VA is still equal to mod VB. So, let us see on the 3 phase side what will happen. This is the 3 phase voltage phasor, line voltage phasors A, B, C, this is M, this is say N. So, as in the previous case, the line current will be IA, this will be still be 2 by root 3 N2 by N1 into I small a. This will still be IBC, this is minus IBC, and IB is IBC minus IA by 2. IA by 2. This will be the current IB. And IC will be minus IBC minus IA by 2. Obviously, the 3 phase currents are no longer balanced, but still they will be given by the same formula. IB will be IBC, which is N2 by N1 IB plus minus 1 by half IA minus IA by 2. This is IA, this is minus, this is IA by 2, this is IA by 2, this current is IBC, this current is IB. IA by 2, hence it is 1 by root 3 N2 by N1 IA, that is equal to N2 by N1 IB minus 1 by root 3 IA. Similarly, IC will be minus of N2 by N1 IB plus 1 by root 3 IA. How much these magnitudes will be? Let us try to see with an example. Say we have a 6.6 kV by 250 volts Scott connected transformer. The leading phase, that is, this is the 6.6 kV, this is N1, this is N1 at 50% tapping, at 86.7% tapping. The line voltage this is VA, VB, VC. The line voltage here is 6.6 kV, and this is the two phase side. This is V small a, nominally this is 250 volts. Similarly, this number of turns is N2. Here this is also N2. This is also VB equal to 250 volts nominally. Now, the load on this transformer on the leading phase, that is on phase A, I have connected a load ZA, which is equal to nominally 50 kilowatt, that is when the voltage is 250 volts, it is 50 kilowatt at 0.8 lagging power factor. And I have connected another load ZB to the lagging phase this current is IA, this current is IB equal to this is 60 kilowatt at 0.7 lagging power factor, that is the load is unbalanced. So, neglecting no load current, we are expected to find out what will be the three phase input currents IA, IB and IC. Obviously, the turns ratio N2 by N1 equal to Vb by Vbc equal to 250 divided by 6600 or N1 by N2 equal to 26.4. Now, if we choose Vbc to be the reference phasor, Vbc to be the reference phasor, this is 6600 angle 0 degree this is VBC, this is VAB, this is VCA. VBC is the reference phasor. Then we know VA equal to 250 volts angle 90 degree and VB equal to 250 volts angle 0 degree. Therefore, the load currents IA equal to 50 kilowatt divided by this is 50 kVA, made mistake, this is 50 kVA at 0.8 and this is 60 kVA at 0.7. So, the load current IA is 50 kVA divided by 250 at an angle of 90 minus cos inverse 0.8 or IA equal to 200 amperes at an angle of 53.13 degrees. Similarly, phasor IB equal to 60 kVA divided by 250 amperes at an angle of minus cos inverse 0.7, that is IB equal to 240 amperes at an angle of minus 45.57 degrees. So, this is VA, this is VB, this is IA equal to 200 amperes and this angle is 53.13 degrees. This is IB equal to 240 amperes and this angle is 45.57 degrees. So, what will be the line current capital IA? capital IA we have seen is given by two by root 3 into N2 by N1 into IA, hence this comes to 2 by root 3 into 1 by 26.4 into 200 angle 53.13 degrees. This comes to 8.75 ampere at an angle of 53.13 degrees. Now, IBC will be equal to N2 by N1 into IB, hence this will be 1 by 26.4 into 240 angle minus 45.57 degrees. This comes to 9.091 angle minus 45.57 degrees. Therefore, the current IB will be equal to IBC minus IA by 2, that is 9.091 amperes angle minus 45.57 degrees minus 8.75 by 2 amperes angle 53.13 degrees. Once we do the calculation, it comes to 10.67 ampere angle of minus 69.48 degrees. The phasor IC will be minus IBC minus IA by 2, that is minus 9.091 ampere angle minus 45.57 degrees minus 8.75 by 2 amperes angle. This comes to 9.47 amperes angle 161.6 degrees. So, if we draw the phasor diagram, we had taken VBC to be the reference phasor, the current IA is 8.75 amperes at an angle of 53.13 degrees. This is the reference direction. So, this is, let us say, current IA. This angle is 53.13 degrees. the current IB is 10.67 ampere at an angle of almost minus 70 degrees. So, this is IB, this angle is 69.48 degrees, the magnitude is 10.67 amperes. On the other hand, IC is somewhere here, magnitude is 9.47 amperes, and this angle with respect to reference is 161.6 degrees. So, what is the angle between different, for example, between IA and IB? The angle is 53.13 degrees plus 69.48 degrees. This comes to between IA and IB, this angle is 122.61 degrees. Similarly, what is the angle between IC and IA? IA and IC, this angle is 161.6 degrees minus 53.13 degrees. This angle is 108.47 degrees. So, we see that when the load current is unbalanced, the current supplied by the 3-phase side in a Scott connected transformer is also unbalanced. Now, one extreme case of unbalance is of course a single phase load. A Scott connected transformer can be used to supply a single phase load. Same connection, this is 50% tapping, this is 86.7% tapping. For supplying single phase load, we connect these 2 points. We connect the windings in series. And this is how at the single phase load is connected. So, the current here is I A, this is the current I B. If we look at the phasors, this is the voltage V B, this is the voltage V A. If we look at the phasor diagram, this is the input side phasor, this is V B, this is V A. The load voltage is V L, I A equal to I B equal to I L here. This is V B, this is V A. Hence, the load voltage is the vector sum of V A plus V B, which is here, this is the load voltage V L, and let us say this is the load current I L equal to I A equal to I B. Hence, we see that this is a special case of unbalanced loading, where the magnitudes of the two phase currents are same, but their phase angles are not same. So, what will happen here? The current I capital A will still be in the direction of I L, but now I B C, which is this will also be the direction of I B C. It will actually be root 3 by 2 times I B C. By root 3 times. So, I B and I C will be, I B will be I B C minus I A by 2. So, I B will be somewhere here, and I C will be minus I B C minus I A by 2, I C will be somewhere here. So, even in the 3 phase side, the line currents will be all in phase. That is what happens when a Scott connected transformer secondaries are connected in series to supply a single phase load. Thank you.